Okay, in regular A-level maths, we saw how we could solve a differential equation as long as we were able to use a technique called separating the variables. In this case, we could separate the variables pretty easily because we can move the g of y function to the left-hand side, and we can move the dx over to the right-hand side. So we have all of the y's together on the left-hand side like this, all of the x's together on the right-hand side like this, and that then meant that we could then integrate both sides, and depending on the function, depending on each of the functions, it was relatively easy then to integrate both sides and finish the question off. In further maths, we are going to look at situations where it is not as easy, or actually you can't, in fact, separate the variables. So for example, in this equation here, we can see we've got dy by dx, which is what's making this a differential equation. And then we've got a function of x times y equals another function of x. So you might think, oh, well, maybe I could multiply through by the dx like we did in the previous example. But if we did that, that is then going to also create a dx here and also a dx over here. And then you might think, okay, well, let's try and integrate through now like we did before. This bit and this bit would integrate easily. This bit here, however, that y, we can't integrate that y with respect to x. So there's a big problem here. You then might think, well, maybe we could divide through by y like we did before, which would be okay here because we'd have a 1 over y dy. And here now we would just have an f of x dx. So that's all okay. This integrates easily, this integrates easily. But then over here, we would have to divide through by y here as well. And then again, we've got the same problem that we had before. We're trying to integrate a y function with respect to x, so we can't do it. So what I'm trying to do here will not work. You can't use a separation of variables technique to solve something like this. So we need to use a different technique. In this video, I'm going to show you how we can spot a pattern. So this is an example of a differential equation that you might need to solve. Something like this, where the separations of variables technique will not work. Now, this is actually in a particular form where we can rewrite the left-hand side pretty easily. Before I show you that, however, you need to basically get good at be really good, in fact. I know you are all already very good, but you need to be even better at using the product rule. So what I would like you to do, just for a moment, just press pause on the video and then practice differentiating each of these with the product rule. Okay, so just press pause, have a go at differentiating each of those. So differentiating x cubed times y with the product rule, then differentiating x to the power 4 times y with the product rule, and so on. You will need to use some implicit differentiation down here. So have a go at differentiating each of those with the product rule. When you're ready, press play, because I'm going to show you the answers and explain. Okay, so when we differentiate the first one, I'm going to differentiate x cubed, which will give me 3x squared, multiplied by the y. And then I'm going to differentiate the y, which will give me dy by dx, multiplied by the x cubed. So that's the first one. Second one, differentiate the x to the power 4, I get 4x squared, times the y. Differentiate the y, I get dy by dx, times it by the x to the power 4. Next, differentiate the y, I get dy by dx, multiply it by the sine x. Then differentiate the sine x, I get cos x, times it by the y. Next, differentiate the y function, I get dy by dx, multiply it by f of x. Then differentiate f of x, I get f dash of x, multiply it by the y function. And then finally, differentiating the g of y function. Now I have to use implicit differentiation to do this. I'm going to differentiate this with respect to y, which will give me g dash of y, then multiply it by the dy by dx function. So I've differentiated g with respect to y to get this, then multiplied it by the dy by dx. So this is the implicit way of differentiating this with respect to x. Then times it by f of x. And then I'm going to differentiate the f of x function, which I can do easily to get f dash of x, times it by the g of y. So that helps us in these questions, because if we can spot something that looks like this, or this, or this, or this, or this, if we can spot something that looks like this, then we can rewrite that as that. This is the same thing as this. So in that example we just saw a minute ago, notice how the left-hand side here, I've got x cubed dy by dx plus 3x squared y. So this is actually the same thing as this. So I can replace that with this, which then makes this really easy, because I can now integrate both sides with respect to x to get rid of this. So integrating this side with respect to x just gives this, because these are inverse operators. Integrating this side with respect to x, and I know that integrating sine gives minus cos x, not forgetting the plus c there. Moving the cos x to the other side, and I get that. So there we go, I've solved this differential equation to give this general solution. And obviously if I was told some boundary conditions, I could work out what the constant c is here. So let's have a look at another example then. This here again is a relatively simple example, because I know I can rewrite this left-hand side as that. Because I know that when I differentiate the ln function, I'll get the 1 over x function that's here. And I know that when I differentiate the y function, I'll get the dy by dx. So basically I know that differentiating y ln x will give dy by dx ln x plus y over x, because differentiating this gives dy by dx multiplied by this. Differentiating this gives 1 over x times by this, which is this. So I'm able to get this reasonably easily from that. In a minute I'll show you how you could get this a longer way if you couldn't spot that this is the same thing as this. Anyway, I can now integrate both sides with respect to x to get this, and sec squared integrates to give tan, not forgetting the constant there. Right, so a harder example, something like this. How could we integrate something, how could we solve this differential equation? Now again, you might be able to spot how to rewrite this. But if you can't, let's just go back to that example over here. And let me see if I can arrange this so we can compare. So I'm trying to compare this and this, this and this, because I'm hoping to rewrite this like this, if I know what g of y and f of x are. So just comparing here, I can see I've got a dy by dx here and a dy by dx here, which means that this 4xy here must be this times this. Okay, this 4xy here is the g dash of y times f of x. And then I'm hoping over here, this is going to be my g of y times f dash of x. So looking at these then, I'm looking at this and I'm thinking, well, I've got g of y here, that's a y, g dash of y here, that's a y function. So what about if I thought that g dash of y was just y, and the f of x was 4x? So I'm just comparing both sides. I'm saying, right, this is a y function. In fact, it's the derivative of the y function. So it makes sense to think that that might be the y there. This is an x function. So it makes sense to think of that as the f of x function here. The key thing then is, does that work over here? So let's check. When I integrate g dash of y, that will obviously give me my g of y function. And when I integrate y, I get half y squared. Similarly here, if my f of x function is 4x, when I differentiate that, I get 4. So now I'm thinking, does that work here? If I take my g of y function and I multiply it by the derivative of the f function, so multiply it by 4, if I times these two things together, does that give me 2y squared? So a half y squared times 4, yes, that does give me 2y squared. So this selection here of f of x and g of y does work. So that allows me then to take that original equation, this, and rewrite the left-hand side as the derivative of the g of y function times the f of x function. I know that when I differentiate this, I would get all of this. Oops. So that is a long way how you can find out what's going to go inside these brackets. Most of the time, hopefully, like you saw with this case, you'll just be able to just look at it and say, right, well, I know that when I differentiate this function, I'll get this. Or similarly, that example we saw before, when we differentiate this, we'll get this. Most of the cases, in fact, it's going to be you looking at the dy by dx here and then thinking, like, what's that function there? That's x cubed. So I'm going to guess it's going to be x cubed y here. I'm looking here, dy by dx. So I'm thinking that's going to be the function here. So I'm thinking y ln x. So most of I'm not going to say all the time, because we've seen an example a minute ago where that wasn't the case. But most of the time, it's just going to be y times whatever that is. So y times ln x, y times x cubed. But it won't always be that simple, as you can see here. Anyway, once you've got to this part here, we can now obviously simplify this a little bit, because you can do the half times the 4 to give 2. We can integrate both sides with respect to x, and that will give us our solution to that differential equation. So there we go. That's how we can integrate these differential equations, where it's not in the form of separating the variables, but it is in the form of basically the reverse product rule.